So the Eurocode then, what have we seen so far? Well, we've seen that we've got tables of how steel loses its strength as the temperature increases. We've seen that we can plot a standard time temperature curve, which tells us about the increase of temperature with time. Now we've got the basic requirement in the Eurocode, and this is that the resistance in fire, and have a look at the subscripts. Fi is for fire, D is for design, so it's the design resistance, and the T is for time. So we could say that this is the fire design resistance at a certain time has got to be greater than the design fire effects. So E for effects, R for resistance. So straightforward stuff. We want the resistance at a certain time, the design resistance, to exceed the design effects. Now, because of those subscripts Fi for fire, we know that both the effects and the resistance are modified by elevated temperatures. We've already seen that the resistance is modified by an elevated temperature. The steel strength reduces. But also we need to reflect that the effects are reduced in the fire condition. Why are they reduced? Well, they're reduced because the Eurocode says it's an accidental situation. So therefore, although we might design an office floor for an imposed floor load of 2.5 kilonewtons a square meter, and then we make that into a design load by multiplying it by 1.5, we must ask ourselves, what is the real load when a fire breaks out? Well, it almost certainly won't be at its full value. It doubly won't be at 2.5 multiplied by 1.5. It won't be at the ultimate value. This is an accidental situation. We just want the structure to not collapse. We want it to not collapse under the actual loads, and therefore there's going to be a reflection that in the case of fire, there's going to be a reduction factor applied to that imposed floor load to reflect the fact that when we have got a fire, probably, on the basis of probability, we haven't got the full characteristic value of our imposed floor load. So here is a reduction factor, eta. If we look at the denominator, first of all, so highlighted the denominator now, gamma G multiplied by the permanent actions, gamma Q multiplied by the variable actions, you should all recognize that as the expression of the ultimate loads or the design loads. In the highlighted box there, if you're familiar with the Eurocodes, you would know that as 1.35 multiplied by the permanent actions and 1.5 multiplied by the variable actions. So that's the normal design loading at ULS. Well, the numerator, look, is the unfactored permanent actions. It's the unfactored variable actions, but notice the variable action is also reduced by a psi fire. So it's a load which is even less than, you might describe it as I have done on the slide, the SLS value of the actions. You might properly describe it as the characteristic value of the actions, but it's less than the characteristic value of the actions, or the unfactored value of the actions, because we're applying this psi fire to the variable actions. So we need to know about psi fire. If we had calculated our design values at ambient temperature according to expressions 610A and 610B out of EN 1990, and I hope you know all about that. If I go back to this slide, this slide is based on expression 610 out of EN 1990. In EN 1990, you have an option. Do you want to calculate your design actions according to expression 610, or do you want to calculate them according to the most onerous of 610A and 610B? Well, if you want to reduce the weight of the steel, if you want to reduce the carbon of the steel, if you want the most effective job, then you would have used the most onerous out of 610A and 610B. If you'd have done that, then your value of eta will be slightly different. Broadly speaking, in the top one, I hope that you would recognize again the denominator. That would be the design value of the actions based on 610A. And the bottom one, the denominator, would be the design value of the actions based on 610B. So if you had done that, then you would use these slightly different expressions. The numerator, still remember, has got this reduction factor, psi fire. We've got the option for psi fire in EN 1991-12. The Eurocode itself recommends that we use psi 2. But here is a really important intervention by the UK National Annex, because in the UK, our National Annex says, no, 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 psi fire should be taken as the value psi 1. And for those of you who are interested, psi 1 is larger than psi 2. So we've got a more onerous situation. So we know that psi fire must be equal to psi 1. And then we go off and have a look in EN 1990 to determine the values of psi 1. There are, in two places, a couple of helpful graphs so that we might calculate this reduction factor eta fire. So you find these graphs in EN 1993-12. You also find them in EN 1994-12. Okay, so here is the one out of EN 1993-12. They are exactly the same. This graph is plotted over on the left-hand side with a gamma G and a gamma Q of 1.35 and 1.5. So they are the recommended values, and they're the values that we adopt in the United Kingdom. So for us here, it's good. I suppose if you're in a different country and you'd not adopted 1.35 and 1.5, then you definitely ought not to use this graph, because that's an important part of the scope. And then down on the bottom axis, look, we've got the QK divided by GK. So because of the K subscript, we know that's the characteristic value, or the unfactored value. So the unfactored value of the variable action divided by the unfactored value of the permanent action. And then we've got different curves for different values of psi 1. And hopefully this is starting to make sense, or maybe it's becoming terribly complicated. But those psi 1s depend on the type of variable action. So let me just flip to the next slide and point that out. So for different categories of use, so I've highlighted on the left-hand side an office area. We've got a value of psi 1 over on the right-hand side of 0.5, okay? But for different things, for example, a shopping area, over on the right-hand side, the value of psi 1 is 0.7. For a storage area, you'll see that the value of psi 1 is 0.9. And I'm highlighting those, ladies and gentlemen, because I'm actually trying to build a foundation for things which are going to come later. We've got different psi 1 values for different uses of building. Really important that we recognize that. We don't have to know these values off by heart, but just try and remember 0.5, 0.7 and 0.9 for different categories of buildings. So if I go back a slide, that's why over on the right-hand side, we've got different values of psi 1, 0.9, 0.7, 0.5. Okay, 0.2 seems a little bit obscure for me. Let's just see where 0.2 comes from. Well, according to the UK National Annex, it doesn't come from anywhere. So I'm not entirely sure why this bottom curve is even shown. But we would find ourselves using the curves depending on the type of floor loading for 0.5, 0.7, 0.9. Okay, so we would work out the ratio QK divided by GK along the bottom. I suppose most of the time it's in this sort of zone. If you think about the variable action that you might use, 2.5 kilonewtons a square meter, maybe. What would be the permanent action to support 2.5 kilonewtons a square meter? Well, maybe about the same, maybe a bit less, maybe a bit more. So somewhere in that sort of area. And for different types of floor loading, you could interrogate those curves. Or alternatively, the Eurocode says you can immediately take the value of 0.65. Well, I don't know what to think about that really. 0.65 is somewhere up here. I suppose we would say it's quite conservative in most cases, although not conservative in all cases. If you had a ratio somewhere down here somewhere, depending on your type of floor load, then it's maybe not quite conservative, but for most things it would be conservative. Personally, I wouldn't do it. I would work out my actual ratio on the bottom axis. I would know the type of imposed floor loading over on the right hand side, so I know what Psi1 is, and I would personally use the actual value. So those are the values of Psi1 again, shown you those already. Here is a particular example. We've got a permanent action. We've got a very high variable action, 5 kilonewtons a square meter. Who would design for that these days? That's crowd loading. We've got a Psi1 value of 0.5. So if I do go back a slide and I remove all my annotations, we're probably in the office area because that's got a Psi1 value of 0.5.